Bhamnagar you found barren lands. Okay, so you need some plants which is salt tolerant, marine biotechnology, marine microbes, marine bioactives and lot of things. And other one which is the huge impact, that is the marine environment. Nowadays, lot of industries in Gujarat, that's a good thing and bad thing for the environment. So you have to be pollution control and environmental assets. But you know that all these things are going on. So this is our institute. So our institute actually Bhamnagar Raja, that is hotel. Okay, so he gave to the CSIR, and that is the building. We have the old building, and you cannot renovate it. Okay, when you cannot break it, you cannot renovate it, but you cannot break it. So it's old building, and we have a small campus, not a big campus. Okay, coming back to my work. So I am working in mostly on seed activation and functionalizations, and we are working on synthesis and API and KSM, and also in the seed polysaccharides, as people have mentioned about the API and KSM extensively. So what we are doing during the COVID pandemic, so everybody has a job. So we got the job for synthesis of drugs, that is the repurposing drugs. What is the repurposing means? The drug is known for something. So you don't have to do the phase 1, phase 2, phase 3 clinical trial. All the toxicity studies are there. So repurpose. Repurpose means we have to use that drug for COVID. So there should be some reason. What is the reason? Because it found that it acts as a serine protease inhibitor and the enzyme transmembrane protease serine 2 to prevent the cellular enter of the virus SARS-CoV-2. So that's the idea. So it will work, and it is works as a serine protease inhibitor. So what we did, we synthesized this starting from, I'm not going in details on this one, fluoroacetic acids and all these things. So we have finally synthesized this drug. So as you know, those who are working in chemistry, you know that there are several challenges. We have synthesized this. This is chemostat mesylate. We have initially synthesized chemostat mesylate, and we did it within 3 months. Okay, that's a great achievement. But to tosylate to mesylate, it was a nightmare. That's the salt conversion. So chemistry, you don't know when it will affect you. Okay, so it took 6 months to establish that simple procedure. Then what we did tosylate to carbonate salt and carbonate salt to mesylate salt. Salt means that you have an amine, so the counter anion is that salt. So we synthesize this chemostat mesylate in 7 steps using all indigenous chemicals, no China dependency. That time, okay, so we have a land border issue. China, you cannot take any chemicals, although most of the chemicals come from China. Without any column chromatography, someone asked that whether you can do industry, you cannot do the column chromatography. So we did it, and we calculate the raw material cost. It was 20,000 rupees per kg. Okay, so if you need a gram dose, so that is 20 rupees. That is economic. Okay, so we have tried to file that patent because it is a non-infringing route. And currently, another one, this is a agrochemicals, which known as spiropyridiol, although it is under patent by Syngenta. Patent will expire in 2029. But we have developed another method, non-infringing method, to synthesize this, and we have filed the patent also in last year, almost a year ago, and we did it at 50 gram scale. Okay. So these molecules also pretend to be a blockbuster agrochemicals. Okay, so it has a applications like in vegetable like tomatoes, oranges, melons, and all these things. Okay, so it inhibits the sucking space like aphids, white flies, and scales. So that is Syngenta's molecule. As I told you, out patent will be 2029, but we are ahead. We have synthesized, and we are looking for industry who will take up this molecule. So coming back to seaweed polysaccharide. So anybody know what is seaweed? Anybody? Seaweed? Seaweed that samundar mein jo samundri shaiwal bolte hain. Okay, so seaweed has an India good thing. We have a huge coastal area. Okay, so seaweed polysaccharides, some things are natural and something we have to cultivate. Okay. So some thing we have cultivated. Our institute is extensively working on seaweeds. We have a mandapam there we cultivate. Okay, that we cultivate the seaweeds. So seaweeds, we have several technologies transfer. I think 35 to 37 technologies already transferred. That is the SAP solution. I am not going in detail on that. So what we are interested, we found that sweet polysaccharides have several polysaccharides. Sweet content like agarose, carrageenan, alginate, mucoidan. These are the different kind of brown seaweed or red seaweed we have. Okay, and these are some impact. So you can use like carrageenan and alginate has a lot of application. Carrageenan, suppose all of you are eating curd, right? So curd is thick, but if you make curd at home, it is not so thick. So they put carrageenan. It forms a gel and it is thick things. Okay. So what we did? So we found that this forms the gel, and when it forms the gel kind of things, you can make it as a film. I don't have the sample. Otherwise, you can distinguish that whether it is a plastic or it's a gel. And we found that these are biodegradable. Okay. The problem when it is from the polysaccharides and they are not thermoplastics. So thermoplastic means what? Thermoplastic means you see all these things, you have a plastic, you heat it and you can seal it. But if it is a polysaccharide, you cannot heat and seal. And these are hydrophilic. Okay, and these are polysaccharides, hydrophilic. Hydrophilic means they love water. So you have to make it hydrophobic. So that chemistry comes. So what we did, we tried to make these molecules so hydrophobic that it will form gel. That means it needs hydrophilic properties also. You cannot block all the hydroxy group, then it will not form the gel. And somehow you cannot improve its hydrophobicity, so you can use as a packaging material. So different kind of packaging materials are there. So by chemical and physical modification, we have tried and yes, sorry. So normal carrageenan film contact angle is 65 degree. So that means it says that contact angle means you put a water droplet in a film and you measure with a machine, that is the contact angle. It shows this angle. So if your angle is more than 90 degree, then you say it is hydrophobic. If your angle is less than 90 degree, then it is hydrophilic. Okay, so for carrageenan, of course, it is 65 degree, that means it is in hydrophilic nature. It loves water. So we changes to hydrophobic. And finally, we got some sheet, some film that is around 125 degree. That's a good thing. And with that, we found some films, not same film has the same property, other films also the elongation property, and some film, the tensile strength is 120 megapascal. That is a excellent tensile strength. So how we prepare? We prepare, that is our Juga way. Okay, so Indians are good in Juga. So we make this. So prepare this solution, and this is an instrument developed by us. Simple instrument. Okay. So there is a rotary blade belt. So we pour our water solutions of the carrageenan film with some additives. Okay, and you can make the film very easily. And with that, this is very new one. What it is when we are doing something, so we prepared a leather kind of material from that similar kind of polysaccharide. Here we did in situ esterification followed by micelle formation, and it forms then the film casting, and we did the drying, and this one we have started everything, means the patent start and everything is done. Okay. So the next one is okay. So now coming back to the main topics, what is that stage activation and functionalization. I don't know, it's not working. Okay. So, you think about organic chemistry deals with the formation of a carbon-carbon or carbon-nitrogen bond. Next slide, next interface. So traditionally, we do the functional group modification. So what is functional group modification? Suppose you have a OH group, you want to do something, you make it OMS wing group, and then treat with a halide, you make that things. Okay. So it was found to be not atomical because you are generating a lot of waste, not stable chemical, and you generate a lot of amounts of waste. And E factor, that is the environmental factor. E factor means how much waste you generate. Or suppose if you generate 50 kg of waste to prepare 1 kg of material, that means your E factor is 50. Okay. And then the selectivity issue and functional group tolerance. Okay, so now when the cross-coupling reaction was developed in 1970s by several mostly Japanese scientists like Suzuki, Hay, Nigesi, so it was a revolution. Okay, so you can prepare biaryl ring and other aryl or carbon nitrogen bond very easily. So it has a huge selectivity and excellent functional group tolerance, but as you need the pre-functionalized substrate, so the term is called atom economy or step economical things. Okay, so Professor Hay, Nigesi and Suzuki got Nobel in 2010. Okay, and when CH activation started, early 1990s, so what happens there? So the step and atom economy is improved. Okay, so that means you generate less amount of waste and E factor is selectivity also is issue, and you have a good functional group tolerance. So if I compare the direct CH activation and traditional cross coupling, the main thing is the pre-functionalization. So that means you don't need a pre-functionalized substrate. Suppose if you are doing with a Suzuki, that means you need a aryl boronic acid with an aryl halide. But if you do the CH activation, so one you can avoid, like you don't need aryl boronic acid, you can do the functionalization. So that's the one thing. It is a step economy, that means you don't have to prepare, environmentally benign and economically attractive. The major important is late stage functionalization. So suppose you are preparing, you are developing a new chemical entity for drugs. So you found very good efficacy, toxicity, and all these things, and that time you thought that okay, if I have a methyl group here, or if I have a halide group here, it might sort better. So you don't have to go back. So if you design the substrate in that way, you can selectively functionalize one CH bond, and you can synthesize highly diverse molecular architecture. But the challenge is that thing, which one is you are thinking the advantage, because you have a lot of CH bond. Okay, so how you can functionalize one CH bond in presence of other? That's the major challenge. Okay, so which one is the advantage you had? That is your disadvantage. So one such way to overcome that, the incorporation of a directing group. So directing group is a ligand. It's an internal ligand. Okay. So what it do? It binds with your metal, and if that metal comes to close proximity to one specific CH bond, which one you want to activate. That means directing groups plays a major role, and then the metal. Okay. So that you can do. So if I talk about, there is a confusion between CH activation and CH functionalization. So CH activation is a specific mechanistic steps. Okay. So where a CH bond interacts with a metal and a carbon metal bond will form. That reaction you can see the CH activation. And the whole chemistry, which one is going on, that is the CH functionalization reaction. So CH functionalization, it might go through CH activation or might not go through the CH activation pathway. Chirocin assisted means a metal center guided to a specific CH bond by the chirocin assisted by a directing group, which one we sometimes call a GPS. Okay, so it acts as a GPS when you want to go there. So when we talk about CH functionalization and the role of directing group, there are several kinds of directing groups. So one such thing is pre-installed directing groups, that means a remover directing group. You put a directing groups and after the reaction you remove it like a ligand. Another is native directing groups. Hello? Yeah. So that means it is in the molecules. So molecules have some functional groups or molecule in a heteroatom. That atom you are using as a directing group. Am I audible? And another one is transient directing groups. Okay. So each directing groups have some advantages, have some disadvantages. Okay. So my research focus on mostly this kind of molecules like naphthalene, quinoline formaldehyde, 8-methylquinoline, alkene and alkyne. So few of them I am going to talk today. So naphthalene, if you think about a naphthalene molecule, one functionalized group is there. So that means we put a DG there. So you have 7 different hydrogen atoms. The challenge is whether you can functionalize selectively of all carbon hydrogen bond or at least few. Okay, so that challenge we took. So we designed and we studied the literature as Bipulbhai mentioned that you have to study the literature. So before him, someone else also did. So we found that if you want to functionalize the C2 position, so you choose a directing group which can functionalize that hydrogen bond. So it is a geometrically accessible. Means your ligands, that means the directing group and metal center, are close proximity to that hydrogen and you can functionalize that. If you think about C3 functionalization, so you need a linker with the ligand. Okay, so that's the big thing. So you can do the meta-CH functionalization. If you want to do the peri, that is the C8 functionalization, so you choose a directing group in a different way and choose choice of metal is important. So all these three cases are geometrically accessible. Means your design of ligand is such a way that you can geometrically accessible that, but rest you cannot. So think about the C4 functionalization. So C4 functionalization, when it is a geometrically inaccessible position, that means okay. So this position which one is bound 1. Okay. So how the strategy is that we choose a catalyst in such a way that it goes to the 1 electron transfer pathway. So what is 1 electron transfer pathway? That means you have this system that a single electron transfer pathway to form a radical cationic species. Once you have radical cationic species, the para to the amide is more reactive position. So you can selectively functionalize the C4 position. So that's our target. We thought whether we can use copper, that is the earth abundant and less toxic material and economic. Not cheap, it's economic. So my student Tapan started this one. So and you have to develop a new chemistry. Okay, so all these reactions we develop, not only the idea, we incorporate new functional groups. Okay, so if you want to incorporate a carboxylic acid group in anything, it's sometimes very difficult because you have to do the cyanation, the strategy, cyanation, and followed by hydrolysis. So we found that CBr4, carbon tetrabromide, can act as a masking carboxylic agent. Okay, so we use copper triplet, potassium carbonate. I am not going in details. And we found that reaction goes and selectively goes to the C4 position. So which one we are expecting that it goes to the single electron transfer pathway. And we have prepared some molecule like fluorescent sensor for cellular zinc, which is a node. We have functionalized that one. And in most of the reactions, what we do all the study to explore its reaction mechanism. So if you know the reaction mechanism, how it works, then you can develop new reactions. So we did the kinetics. When we did the kinetics to HPLC, we found something else is forming and going down. That's in the green color. and we found that it is the intermediate orthoester is forming. Okay, so from that and some other experiments like kinetic isotope effect. Anybody knows what is kinetic isotope effect? So kinetic isotope effect means, so hydrogen, which one is the hydrogen isotope? Deuterium, right? D. So you prepare a molecule with hydrogen and you prepare a molecule with deuterium. Okay, and you did the two parallel reactions and check the kinetics. That means reaction progress with time. Okay, so from that kinetic isotope effect, so you will get two rate constant. Okay, one is for KH, another is for KD. Okay, so if your KH by KD, that is called kinetic isotope effect, is more than 1.4 or more than that, then you can say that hydrogen bond cleavage is the rate determining step. What is rate determining step? So any of your reaction, there is several mechanistic steps. Which one is the slowest step that determines the rate? Okay, so that's why we are doing the kinetic isotope effect to know that whether our CH activation state is the rate determining or not. There are several other steps like oxidative addition, reductive elimination, all these steps. Okay, so we found that KH by KD is 1.04, that means it's not the RDF. Okay, and then we study the radical inhibition study. So what will give you the radical inhibition study? So in the reaction medium, you put a radical inhibitor. So if your reaction pathway goes through a radical pathway, that the inhibitor will trap that radical. It will react fast, like butylated hydroxytoluene or TEMPO. So they react with the radical species. Once that radical species is reacted, that means reaction will quench. You will not find any reactions or reaction will be dropped. As well as, if you are lucky, you can trap or isolate or identify that radical species trapped DHT species. So we have identified that also, and we designed some of the substrate to know whether the role of nitrogen atom, like which one we use the directing group. So we use tertiary amide instead of NH. We use oxygen, or there is instead of pyridine, we don't have the pyridine, and there is phenyl and simple amine. And we found all these are unsuccessful. And with all this data, we proposed the reaction mechanism. So reaction mechanism is proposed that copper triplet reaction with your substrate form a complex, and that reacts with your CBr both, generate a CBr radical, then the single electron transfer as we proposed. It forms a radically cationic species, they both the radical reacts, and then the aromatization. And followed by, when you got the CBr3, it goes to the methanolysis from the orthoester, which one we have identified, and followed by the elimination of methyl bromide and methanol, you get your desired carboxylated product at C4 position. So we are interested to functionalize different positions also. So Kappan also developed another reaction with the copper catalyst with some other additive like sodium carbonate at the C8 position elimination. And he did the sequential functionation. Sequential functionation means, so first he did the amination reaction followed by carboxylation reaction, and you can see that the pathway, that means it was not getting other dissociative product. And path B also followed by carboxylation and amination product, and we found both the reactions that overall yield almost same. And there are several substrate scope, and when you incorporate a directing group, you have to remove. Okay, so directing group, as I said, directing group the removal. So we have removed the directing group, and you can synthesize that 1,8 diamine kind of molecules. Similarly, Nilesh did this work. I forgot to put his photo. So this one also the same substrate, the naphthylamine, and with cobalt bromide we did the sulfoxymelation. So sulfoxylamine preparation is difficult. Okay, so we prepared it with the cobalt catalyst, and we did all the control experiment to know the reaction mechanism. We did it, and here are the examples of variation of all these things. So that is to know whether your reaction is really good. So you have to do a lot of substrate scope, lot of functional group, and other tolerance, and the steric and electronic both factors you have to check. And we did it, and we found that this reaction was well. There is the only one case with the 3G. Here you can find that when the position of methyl is ortho to that amide, it does not work. So why it does not work? Your molecules is flat molecules, but when you have a methyl group, So that NH bond through the your pyridine, that means pyridinamide part, it twisted away from the plane. So okay, as it twisted away from the plane, all the metal is coordinated, but your that carbon hydrogen bond is not in the same plane with the metal center. So that means it was not activated. So that's why we are not getting. And we published this work in JSC, and we are lucky enough to get the front cover page of this. This one is more interesting. So when we did the situ functionalization chemistry, so situ means here also we have developed a new reaction. So we incorporate a tertiary butyl ether. Okay. So in synthesis of inert alkyl aryl ether, that means tertiary carbon with the oxygen atom is always difficult challenge. Because whenever you do, if you know that there is a chance of elimination and all these things. Okay. So mostly people did use the carboxylic acid and do the decarboxylation, generate a radical this side, the red color, electrochemical decarboxylated, and do the alkyl one. Both the way, either photochemical or electrochemical, they did in that way, and you can generate the aryl alkyl ether. Because these aryl alkyl ether are important in pharmaceutically important molecule. So we found that if you use tertiary butyl peroxide, tertiary butyl peroxide, it can cleanse that one, and we thought of this. So we have the idea that we can generate with copper a single electron transfer radical species. So when I talk about the radical species, so I talk that when you have a radical cationic species, carbonation is more reactive. But if we can do that ether here complex with the copper, so there is a chance that intramolecular transfer can happen, not the intermolecular. That means this radical not from the solvent. So that happens, and we found that it goes through this pathway, and it is not only working for the naphthalene, it works with all polyene systems. Okay, even with the simple arene systems, with benzene systems, and with the directing removal, you can synthesize free substituted benzene. Here, one example, you can do the naphthalene, you can do the pyrene, and all these things. So when we talk about naphthalene, so similar system is the quinoline. If you think, but you have one nitrogen atom more, but nitrogen plays a crucial role. So when we talk about that naphthalene single electron transfer goes to the C4 of the naphthalene. So quinoline can also do this kind of chemistry. Okay. So with this idea, we thought why we should not do the carboxylation reactions, which one is not by in our lab. So that time we don't have the photochemical setup. So we prepared by ourselves. As we said, we are very good in jugaad. So we procured LED bulb and with a wooden box, but incorporate a fan, because the fan is needed, because if you heat the bulb, so temperature will generate. If you have a cooling fan, so that means circulation of the air, the temperature will be at the room temperature. So with that cooling fan, we prepared a photochemical box. Luckily now currently we have procured a reactor also. So Chiranjeev did the same with the quinoline with a photocatalyst, ruthenium complex, and we did the carboxylation reaction. And in this case, what he did, he prepared 77 examples. That is a huge example. Those who are working in organic chemistry know preparing 16 or 18 compounds is huge. Chiranjeev is so hard worker, he prepared 77 examples. So all these reactions goes very well. And we did all the control experiment. Here also I just mentioned that this does when we did with TEMPO and BHD reaction does not go through. That means it goes a single electron radical pathway, and we have trapped that by HRNS. Stage by stage is 1.04, that means that is the not determining step, and we have isolated some of the intermediates, and this is the proposed reaction mechanism. When we did this reaction mechanism, if you go through, you can see there is no transition metal complex with your ligands. Okay, so that means with your directing group, there is no, so it just ruthenium in presence of light, it excited, and one electron transfer with the name oxidized, and CBr4 goes to CBr3, and that oxidized species is reduced, that your uronine amine to your radical cationic species, and you got the product. So as it does not need, so we then explore whether it works with other aromatic systems. And indeed it works, and he synthesized all the possible which one can available in our lab, and he prepared most of the chemicals and got excellent yields. So when we are doing all these things, most of the things are described in planner. But if you think about the medicinal chemistry, so medicinal chemistry one term is strict from Catalan. Strict from Catalan means incorporate some of the sp3 group. Cannot do all these things because a lot of chemistry will come. So we think and we found that several succinamide motifs and especially phytocyclic compounds are available in a lot of bioactive molecules. And then we designed substrate like this with the melamine, and if you run the reaction, then how much? Yeah. So there are several kinds of reactions can happen. One reaction is the Michael-Dye-Pattison reaction. It is in 1,4-dicarbonyl system. So Michael-Dye-Pattison reaction, that the product is Michael-Dye, not the reaction is Michael-Dye. Okay. Then there is a possibility of CH spiral reaction. Another is NH1 spiral reaction, and we have developed another reaction, CC spiral reaction. So here also we use the photocatalyst, but here the trick is metallophotocatalyst. What is the role of metallophotocatalyst? So your metal is actually the catalyst, and photocatalyst what is doing? So when you do any metal catalyst reaction, so you need an oxidant, okay, to reoxidize that metal. Okay, so it goes to the when it is the reductive elimination pathway, you have to oxidize it and it goes back to your active catalytic system. So here we use a photocatalyst which can go through a single electron transfer pathway. Okay. So we choose cobalt acetate, that is the 3D transition metal catalyst, and using Y as a photocatalyst. The advantage of cobalt acetate, it is a 3D transition metal, so it can go through a single electron transfer pathway. So if you have a 4D or 5D, it mostly goes to 2 electron transfer pathway. So we use 3D transition metal which is economic, and we found that reaction goes very well, and we got the phytocyclic compound. So we have lot of substance scope in these cases. And we explore the reaction mechanism in all details, and here we have even identified a complex, cobalt complex, the CH activated complex. And we propose the reaction mechanism. As I said, we propose the reaction mechanism. That means if we have some other data, the reaction mechanism can change. Okay, whatever the data we have, we found that this is the possible way to explain these results. So cobalt to form the complex with your and then using Y goes to the cobalt 2, cobalt 3, and then the CH activation pathway. So we put it as CMD. CMD means concerted metallation and deprotonation pathway. So that is the concerted things, and hydrogen and metal for bond formation. Then the insertion reaction followed by beta hydride elimination, you generate again double bond, then intramolecular insertion reaction, and finally with the reductive elimination we got the product. So changing next is changing the directing group. So we use a directing group, we change with directing group, and Raj did this work, and he found that when we use the cobalt acetate with using Y, it does not get the product. So this time, changing the ligand also is not working. Then we use the silver phosphate as a oxidant, silver oxidant and sodium bipolate. So it is in the thermal condition, it works well. And we have synthesized several other spirocyclic compound with isoindolate. Thermic, who is present here, hit it. Okay, let's check. Not with the melamine, let's check with the acrylate. What will happen? With the hydroxide directing group, so there is no spiral annulation. That is the addition of this, although we are getting a cyclic compound. So what he did, he said how to apply this chemistry. So we did these reactions, we got this product with the palladium catalyst, and followed by reaction, we make a molecule which is analog to a drug that is called plasminacrone. And we developed the reaction mechanism, and we have identified that here palladium and copper plays a dual role, and from this complex, which one we have identified very fast, and got the product. So this chemistry, actually, we got this binary reaction, we got this kind of cyclization or elimination reaction. In this case, what we thought, if you use the carboxylic acid more and a bulky carboxylic acid, it might go through different reactions, and indeed it goes through a different reaction with the rhodium catalyst and acid as an additive. We found the first time we have reported that it is a CC unrelated product, and this kind of molecules is not reported. So we have filed the patent first, biological evaluation is going on, and later on we have published this paper. And this is the reaction mechanism. It is goes to the diradium complex, and all these mechanisms are, we did lot of kinetics, lot of other studies, and then we propose the reaction mechanism. And this is the very recent one. This is also by Raj. So instead of spiro, cyclic compound and all these things, so we use isocyanide as a substrate. Similar strategy, but ligand and catalyst is different. We use the cobalt catalyst, and we synthesize these benzoindole. Benzoindole means we have synthesized. These are the several known drugs unknown with this structure, and easy way we can synthesize this. And one advantage of this reaction, this is the picolinamide part, which one is the directing group, in situ removal. So you see the product, there is no picolinamide product. So these are the substrate scope. I am not going in details, and we get the variation of pyridine ring, variation of naphthalene ring, several functional group. It works very well, except when you use aryl isocyanide, it does not react. Only react with cyclohexyl or cyclopentine isocyanide. So these are the reaction mechanism steps, and this is the reaction mechanism step. Okay, so overall, with copper or cobalt catalyst, we have selectively functionalized, especially naphthalene, in C2, C4, and C8 position. Now, in last few minutes, how much time I have? 15 minutes. So last 10 to 15 minutes, I will discuss about the native directing group functional group of reaction. So as we discussed about the directing group, so that means you need a disconnection and removal of the directing group. So if you see that that's the advantage of, so if you have a functional group, something, or suppose you have a pyridine ring or pyridine ring, that nitrogen, can you use that one as a ligand and functionalize your molecule? So that's the challenge. So you don't need any external functional group, you don't need the removal, so you increase the atom efficiency and state tubular. So we took quinoline carbonaldehyde. So quinoline carbonaldehyde means it is 8 position as a aldehyde group with quinoline. We thought whether or palladium complex can do the reaction, because not all the cases you can use copper and cobalt. Okay. So if you can synthesize this kind of diamond complex, so you can functionalize that aldehyde. So aldehyde, if you want to synthesize aldehyde to ketone, how you will synthesize? You will need a nucleophile like methyl magnesium bromide. You react with that, it will go to alcohol, then it will oxidize, and you will get the product. Okay. But if you activated that one, okay, so when we say carbon metal bond, the reactivity also unpolar. Okay, the reactivity changes, and you can do the coupling kind of reaction. So we did that, but there is a challenge. You see the palladium with the carbonyl bond. Okay, so there is a chance of decarbonylation, because we did the carbonylation reaction with the palladium also. Like when you are doing the formylation, hydroformylation reaction with the syngas and all these things. So metal carbonyl bond is formed, and the decarbonylation has a chance. So there is a strategy. There is a possibility that you can get the decarbonated product. So we screened a lot of things, and finally found we initially start with solvent toluene, and it does not work. So So couple of cases I have the examples and the preview of the result. It is showing 14 to 15 result. Trust me, we carry out almost 100 reactions. We establish a reaction pathway, and many times it failed. Okay. So with the toluene, it does not react. DC 10%, 1,4 dioxane, amyl alcohol is not 1. Okay. So and you force your student to do more. So when there is a negative result, they don't know. Sir, आपका idea काम नहीं करेगा. Okay. So we changed. We found that HFIP, that is hexafluoroisopropanol, it's working. So why it is working? We found that HFIP is an acidic solvent. Although it's an alcohol, but as you have a foreign group there, so you have hydrogen is acidic. Okay. So then we idea, okay, let's use trichloroethanol. We found trichloroethanol is working, and we found acetic acid is the best solvent for this. Although acetic acid generally you have a challenge because acetylation can happen. Okay, so you are using palladium catalyst acetic acid, and we found that acetic acid work. Although acetic acid is not so nasty solvent, but we can handle it. Okay, so we found the keto compound, and we got all this product. And we found here, that is the red box, when you have a nitro group. So the reactivity is less than 10%. That means electron withdrawing substituent does not react well. But to make it general, so whether we can do some reaction, whether electron withdrawing group also work. So we found what are the other arylating source which work. Because we use only aryl iodide, we found aryl chloric acid does not work. Aryl iodinium salt is working, but the interesting thing is the counter anion part is a major role. Because if you have a chloride or nitrate, it does not react, 0%. But when you have a less nucleophilic counter anion, like PF6, 48, it works very well. And as it works with aryl diazonium salt. Okay. So then we found, okay, so aryl diazonium salt we can prepare easily. And we did this reaction and we found this reaction, nitro groups work very well. There is the red color, red is 84%. And as well as OME, which is the electron donating substituent, it will be slow. So that means both reaction mechanism pathway is involved, or something else is happening. So to know this, we did a lot of control experiments. I am not showing here. So as you know, this palladium complex is formed, then aryl active oxidative addition is formed. But for the aryl diazonium, it goes through a radical pathway. So aryl radical is forming. So then it traps the radical and followed by the similar pathway, it goes through. For the aryl radical formation, so your electron withdrawing substituent helps to stabilize that, and you are getting better reading. So we did it in the thermal conditions. So we have a photochemical setup and all this thing. So we thought whether we can do at room temperature, because room temperature reaction is always important. Okay, if you can the reaction in room temperature, so we use the blue LED with the palladium triplet and Xanthos as a ligand, because here we need a ligand, and we found that similar reactivity, and we can synthesize lot of keto compounds here. And it works with other aryl source also, but the yield is little bit low. And we did the control experiment because we have to establish the reaction mechanism. So we found that it goes to the radical pathway because we have trapped the radical, and when we identified the organometallic phosphorus complex, so here we can find that phosphorus has phosphorus and phosphinoxide, so that mass is matching. Okay, that to confirm that we did the 13-1 phosphorus NMR. So that phosphorus NMR also indicates during the time interval NMR, we found that the first ligand initially you did that, but when you light irradiated, we found two peaks, the entry C. One is for phosphorus PPSP, another is for phosphorus oxide. Okay, so then we literature we carry it out, and we found that it goes to the phosphorus oxides, this kind of semilamine ligands. And we check the UPR static. So UPR indicates from the G value, so there is a formation of carbon radical. G value is 2.0042, and we propose this reaction mechanism. Similarly, when we did all these ketone things, our idea is that as we activated the aldehyde, we can synthesize amine. So instead of iodide, you need an amine. But if you think about this condition are always little bit changing. Because when you do the same condition, 90% chances you will get low yield, or you have to optimize the reaction condition. So we did it, and we synthesized a lot of aryl amide or aliphatic amide, and This is the reaction mechanism. Here we found silver plays a role because this is the silver acetate CH activation. That complex was identified by mass, so that's why we are proposing. And so we are working from 2021 from this project, and we propose that this is the diagonal complex, and in 2024 the rest got crystal. The same things, but you have a parallel bond is there. Okay, that's nothing, and it is a sandwich complex, not like the fat molecules. Okay. And we did the esterification reaction, so similar strategy, and it works with all the substrate, and the best is we can incorporate the safety groups here. So dichloroethanol also goes for these esterification reactions. Okay. So when we did the aldehyde state functionation, I think I have a couple of minutes. So we thought, why not in methylphenolic? Similar substrate, if you have a palladium, it can activate that state bond, although it is a sp3 center. So we did it, and we found here that when you did this reaction, the challenge when you are using acetic acid, so you got the acylation product, acetylation product there, the entry 4. And we screened the solvent, we found that you need palladium, you need silver, and you need some ligand, and we found that acetic acid and HFI solvent, this charge is optimum with triphenyl phosphine as a ligand, and we got that dual CH activation. What is dual CH activation? It means two hydrogens is activated simultaneously, one by one. That's the dual CH activation. And we did a lot of substrates with excellent functional group tolerance like bromine, double bond, triple bond, other things, and we study a lot. And this is the control experiment. So when we did the deuterium exchange, what is the deuterium exchange? So you have a reaction, so your carbon metal bond is formed, you know that. So if you put deuterium, your bond is reversible. So that means the bond will break, like you have a D2 or C2 system, so some deuterium will take. Okay. So in your NMR, when you check, so you will get less amount of hydrogen peak. So there you can say, okay, deuterium exchange happens. And what indicates it? It indicates if you have deuterium exchange, that bond breaking is reversible. So once it comes, it might break and again form. Okay. But we might found no exchange, that means CH1 cleavage is irreversible, and it does not go to the ACT pathway because we use the radical inhibitor. We got the product, and we identified the palladium complex, that is very important to identify, and several other complexes also we have identified, and we did the Hammett correlation study. So Hammett correlation study indicates the electronic nature of the influence of the electronic nature of the reaction. So we found that the electron donating group stabilizes the positive charge of the returning state, that's why slope is negative. So that means if you have electron donating substrate, it will react better or it will react faster. Okay. And with other control experiment like reactivity and other things, so like benzoic acid, we need no reaction. With aryl iodide, we got different kind of reaction. So we propose the reaction mechanism. It is, I said, dual CH activation. So the first CH activation takes place there. We have identified, followed by reductive elimination. This is the product, and then by second CH activation, and we got the lactone in the product, and we have published last year it is in organic letter, and we are lucky this one also got the cover page. And finally, the last one, which one we have recently submitted. So we did it earlier, we did it with whether we can do the same things with the ketone. Okay. So that idea comes, we did the similar kind of reaction. So ketone has a different reaction mechanism because when ketone it goes to ketone enol or ketoenolate. So when we did reaction, we found that already in 1997, Bhupal Hardik, they have reported some ketone enol catalysis reaction for the annihilation. But we want to use bifunctional reagent because we used previously, so that means we use iodobenzoic acids. So whether we can do the first annihilation and followed by the which one is the carboxylic acid group, that intramolecular reaction will become a lactone. So here, instead of that lactone, we have prepared another lactone which is isochromar. Okay, indeed it works very well, and we have a lot of substrate scope, not this selected. The thing is, you need a atom which contains the nitrogen. You check with oxygen, sulfur and other, it does not work. But any, not only the quinoline, isoquinoline, pyridine or methylthiazole, it works everywhere. And we got the product, and this is the reaction mechanism, as I said, in all these things. Okay. The interesting thing is, here we found that carbon hydrogen deuterium exchange. Okay, so if you do this with the deuterium, you can see 90% deuterium is exchanged. That means only 8% hydrogen is given. In presence of palladium, it is little less because palladium is bonded there, so it is 48%. When you do this same reaction in B2, we found that bond, which one is the critical one, 25% deuterium exchange, so that bonds are reversible. So, with all this idea, in all other control experiments, we propose this reaction mechanism, kind of similar. The palladium goes to the ketoenol mechanism, and first the oxidative addition to the right, and this complex is which one we identified by SIMS and followed by the intramolecular electronation. We got this isopropyl product. So, thank you all, and and rust and some part of the hermic and I like to thank thank you all. I love to answer if you have any questions. Unfortunately, no. So, which kind of solvent? If you choose a solvent, you have idea whether I need a blood solvent or not. You need a acidic solvent or aquatic solvent. So, from the literature of so, here we found that in the last stages, the palladium catalyzed reaction. So, to utilize all these things, you need an acidic solvent. Okay. And if you go to the last one, so if you found the strongest acid, other than mineral acid, is the strongest acid, and it works with that. In this case also, acetic acid gives us low-yield or acidulous. So there we found that you need in this palladium catalyzed reaction, you found that acid as a solvent works best because of the complex composition and in the complex. So like HCl, only organic acid. So that's what we can do. We are very about which is decay I think around
These are the main relations, right? So can we use the transition metal in that reaction?
Several transition metal we can use. We have also screened several transition metal. Other because we are doing one is the palladium can use. Okay. Some other copper and industry also doing because not the cost, main important thing is presence of this metal in your drug molecule. So when we are doing the drug molecule synthesis, we try to avoid toxic. So that is one important thing. So impurity profiling is important. Okay, so palladium you can reuse, although we are doing in a very small scale. We are not so rich that we can use. So we are doing catalyst to 5 milligram scale catalyst. Amount of 2 milligram scale. Okay. So that we are managing. Okay, so some cases we cannot avoid other than palatine, it will be complicated. Yeah, yeah, yeah. I thought to bring some materials, but so you cannot actually, if I have, then you cannot distinguish between. So this one is a different chemistry actually. So what we do is we for a polysaccharide, we control the one you pronounce the ester, and it puts some agent which can form the micelle. So once we form the micelle, that time you can see the color now form, and then you can use different color of dye, and then you can color the material, and when you cast, it forms another. Otherwise, it generally comes as green. So like for so here I have come and I had all these things that we and all these things. Yeah, these are right. We are working. Properties we are taking with similar, right? Okay, so we are doing developing material. Commercial is a lot of studies we are doing. So as we found that we need to find the trying to change the properties or improve the yeah, we are the there are thousands of directing groups. Okay? So yeah, so what? So generally, I do two or three different types. One is another is vitamin, another is directing group. We are using inner directing, another inno directing. And we are targeting that with on 5 members, maximum 6 members. 5 members is good and easy. So that's the criteria. And then when we do the reactions, so the new chemistry, so that the second part we want to incorporate, like we want to do suppository, so that if we want to do the suppository structure, this one is unexplored, and all this as we are working for 2 years. So when you to lab knows that okay, this chemistry can work for one. Suppose some reactions you have a byproduct, and your senior is not interested, so why do you? And next one person also is interested because this will give you a product, and I use this to make that will be. Students.
Sir, just to ask, like in last 2 to 3 slides, you told that you use the one heteroatom like nitrogen, and you told that only nitrogen with that you can run that reaction, but you cannot use that other heteroatoms. Then what is the reason behind it that you didn't use that?
Okay, so the last one you are saying that nitrogen as a heteroatom, that is a coordination property. So instead of nitrogen, if I use sulfur or oxygen, so it does not bind with your metal. You need a metal nitrogen bond event conversion. Okay, so that is not working. Okay,
Because
so
they all have lone pairs of electron. Even the nitrogen is one. Nitrogen have one lone pair, but oxygen have two lone pairs.
Yeah,
Electronegativity
true, but
also
if you
same.
think about it, so the bonding, if you have a nitrogen palladium bond and palladium oxygen bond, it not tuned for that reactions.
Okay.
In some cases, alcohol with the palladium, it can coordinate or carboxylate with the palladium, although as oxygen, it can coordinate. We found that carboxylate coordinate.
भेजा
I'm a research scholar in Saurashtra University. I was in PhD under Dr. Professor N.K. Shah. And right now I would like to introduce to my research work, that is zinc molybdenum nanocomposite, and it's an efficient and reusable catalyst for the synthesis of 4H bioderivatives. Yeah. So basically, what I'm doing in my lab, what I'm doing in my research is I'm synthesizing Zn molybdenum nanocomposite synthesis via Solgen method, and it is a catalyst. It is a catalyst for the synthesis of tetrahydrobenzopyrene derivatives. Now, what is the advantage of this catalyst? It is that it is recyclable up to 4 cycles. Now, the first question arises, why I have chosen zinc and molybdenum nanocomposites? We have so many catalysts right now, then why I am synthesizing a catalyst? So, to answer that, why I am synthesizing is that, now we all know that in multi-component reaction, what catalyst that we are using, either acid catalyst or basic catalyst. And what is the disadvantages of that? Acid catalyst that we use, it is a very, for acids that we use or acid that it is a very harsh condition. We cannot recycle it. Then sometimes it takes longer reaction rate. So these are the limitations, that longer reaction times, harsh condition, poor reusability. And what I have synthesized, it is a material that has a very high surface area. Definitely, it is cost. Definitely, it is reusable. So it is nice. It has an enhanced catalytic activity, and yeah, it is fast, and it gives me a very high yield. So it is a very better in comparison with the conventional catalyst that we are using right now. Now the second question arises that I am synthesizing this catalyst for the multi-component reaction. Why I have chosen multi-component reaction? So to answer that, yeah, 4H pyrene derivative, I am taking multi-component reaction for specific 4H pyrene derivative. Now why multi-component reactions? So when we are doing BSc and MSc in labs, we do a very small reaction. But in pharmaceutical companies, in industry, there are bulk reactions. So we need something that has an industrial relevance. So multi-component is a one-pot synthesis. It is atom economical. So I have chosen this multi-component reaction. And why 4H pyrene derivative? Because this 4H pyrene derivative has a very great biological application. It shows anti-cancer activity, antiviral, antibacterial. It shows applications in Alzheimer's and Parkinson's disease. And in physical chemistry application as well, it shows optical and fluorescence activity. So it is good. Now, I have synthesized it, what I have done. Now the main thing is how I have done it, how I have synthesized it. So to answer that, I have synthesized zinc and molybdenum nanocomposite. But to synthesize that, first I will have to synthesize molybdenum nanoparticles, zinc oxide nanoparticles, and in the first slide I have told you that I have used the method Sol-Gel method. Now to synthesize nanoparticles, there are many methods, but generally people use Sol-Gel method because it is done at a very low temperature. So we don't require a very high temperature for the synthesis of nanoparticles. Now in the Sol-Gel method, it is a wet chemical process. What we are doing is that a liquid material that is called Sol is gradually converted into 3D network-like structure that is called gel. So it is a Sol-Gel method. And how in water? So in my case, the solvent is water. Then what will I do? I will introduce it to the hydrolysis. Then I will do the condensation. Okay, I have done the hydrolysis, I have done the condensation. And then I will get my nanoparticles. Now, after the nanoparticles are formed, we will have to calcinate it. That means for the, what I am saying is, we have to form a particular streaming network. And how we are able to achieve it? So we will need it to give a certain type of temperature. So for the molybdenum, the temperature is 600 degrees Celsius, and for the Zn, the temperature is 400 degrees around. Now after synthesizing this 4 nanoparticle, the simple thing what I will do is, I will take a mortar pestle, I will grind this 4 thing, and I will get the Zn and NO nanocomposite. So this is how I have synthesized my catalyst. Now, the catalyst is formed, but how will I characterize? So for the characterization, I have done powder XRD. It is still under process, so I don't have the data of this. So I'm sorry about that. I have the FTIR data, I have the SEMTEM data, and EDS data. Now, the nanoparticles are formed. Nanoparticles has a range of 10 raised to minus 9 centimeter. So the same thing study will tell me the exact size of my nanoparticles. So this gives me the idea of that, and this graph shows that my average particle size is 77 nanometer. So it falls under the ratio of nanoparticles. So this confirms that the catalyst that I have synthesized is nano. Now, this is the spectrum, FTIR spectrum. Blue line and red line is the molybdenum oxide FTIR, and the green one is Zn. In the first two, you will see a similar pattern. This 2355 is the atmospheric carbon dioxide, 13908 carbon dioxide, but these 3986 and 897, it is a particular characteristic spectra for MO double bond oxygen, and 652 is a particular band for MO, O and MO. Now, for this is atmospheric carbon dioxide, this is my carbon dioxide, and 438 is a characteristic band for ZnO bond. So this confirms that my nanoparticles are formed. Now, this same data gives me the particle size. This confirms the structure. Now I will need the percentage split. So this data, if we are performing same data, then same data is a half thing. If you want to complete the whole research, you will need this EDS diagram. So EDS diagram will give us the percentage weight. So this confirms that my compound has the elemental composition of oxygen, zinc, molybdenum, and these are the percentage weight of that. Now, I have told you that I have synthesized a catalyst, but does it really work or not? So yes, it does work. This works in 3 component reaction. I have taken this reaction, dimethyl aldehyde and melanonitride. If I am not adding my catalyst, I have a whole different table of that. Yes. If I am not adding any grams of my catalyst, then it will take 180 minutes and yield is 0. But if I am adding 0.01 gram, the time is 30, yield is 36. 0.02 gram, time is 10 minutes and yield is 16 inverse. If I am adding 0.0 grams, the time is 8 minutes and yield is 89%. If I am adding 0.05 grams, time is 8 minutes and yield is 89%. That means I will need 0.03 grams, time is 8 minutes and 89% yield is my optimized situation, the best condition. Now, I have also taken different solvents to check the reaction difference. Now this shows that ethanol has the best yield, that is 89%. Now, my base which is the green solvent, so it's nice. 80 degrees Celsius temperature, 0.03 grams of catalyst, and reaction time is 7 minutes. So this is my application of the catalyst. Now, in the first thing, I have told you that it is a okay. So this is how I conclude. It is recycle up to 4 cycles. In the first cycle, the 96% yield, second 94, third 87, and fourth cycle 79% of yield. So here I conclude my research. I would like to acknowledge the Department of Chemistry of Rajasthan University and really Punjab for all the data. And yes, definitely shows. Thank you so much. Any questions? Yes, sir. Sir, I'm not able to recall it right now.
So we give any three multi-component reactions which are very famous. Anything of it.
Ugi reactions, Ugi reaction, Keith reaction, and what one I want to equal right now.
What your
Yes.
is you should know the reaction. What are domino reaction? Domino reaction.
Domino reaction.
Next to our project Tejas Wadhar, Department of Chemistry School.
Good afternoon. First of all, my topic is digital. Myself, British Bose. I am research scholar at Saurashtra University and the guidance of Dr. U. Bhattacharya. And my topic is liquid crystal. I am working on influence of orthotrifluoromethyl substitution on the mesomorphic and thermal behavior of azoester liquid crystal, experimental DMT studies. Basically, I am working on liquid crystal or to synthesize the liquid crystal which are of low melting. Actually, there are many applications of liquid crystals, but some of them are only applicable if they are low melting. If the melting is high, then we will face their applicability. Introduction. I have synthesized this liquid crystal. Basically, this is structure of liquid crystal where I have imposed CF3 bulky group at the ortho position of azo. Now, liquid crystals are unique materials exhibiting both rigidity and molecular order. Basically, when liquid crystals are formed, they are possesses some molecular order that is like solid type, and also fluidity that refers liquid type nature. Enhancing responses to external stimuli such as light, temperature, and electric field. When we place this material in temperature hot plate, they got arranged in a particular direction that possesses magnetic, limatic, cholesterolic, extra many type of phases. Here, when we have synthesized this compound, we have compared with para-substituted CF3 group. While para-substituted CF3 derivative often exhibit high melting and narrow mesomorphic ranges due to strong molecular tagging. Ortho substitution can introduce steric effect that lowers melting transitions and modify dipole orientation. When we impose bulky group at the ortho position, it inhabit to the packing arrangement of liquid crystals. It lowers the melting point, which is our aim to synthesize. Here is the synthesis. 4-hydroxybenzoic acid react with alkyl halide in the presence of strong base K oil. We have prepared 4N-alkyl oxybenzoic acid, and then diazotization was carried out on 2-trichloromethylenediene with phenol using conventional method as in for information, and we get 4-hydroxyphenyl azo 2-trichloromethylbenzene, which is liquid in nature. That is our primary success to synthesize low melting liquid crystals. Actually, when we preparing liquid crystals, we should note that all the starting materials, if those are on liquid state, there are many chances to prepare low melting liquid crystal that we get low melting liquid crystal. So part A and part B, with BCC DMAP coupling, we get this final structure where CN3 is imposed at ortho position of azo group. Here is QM analysis. In polarizing optical microscope, we get this data where smaller alkyl like C3, C4, 5-member, 4-member, all chains are possesses only monotropic in actually they are actions of symmetric phase and directly getting crystal to I actually I am sorry. This is symmetric, that is liquid crystalline phase, that is I represent isotropic in nature. That means all these compounds get directly liquefied, like we are melting the compounds. But C7 with higher homologous, we are getting monotropic phases on cooling only. So basically, I have prepared low melting, but unfortunately, the anisotropic nature is closed, which is possesses in monotropic. So in this case, C7 compound, which is my lowest melting compound, that possesses 58.5 melting, that is quite low. Actually, my aim is to synthesize at room temperature liquid crystalline compound, but we are getting minimum of 58.5 right now.
फ्रीलांसिंग છે
These
डायरेक्ट
are
जॉब पर
textures
जाओ
of PM. So C7 homologous, C8, C10, and C14 homologous. These are symmetric phases. This is conformation of liquid crystalline compound. Initially, DSC was carried out in heating and cooling both scale. As my compound is monotropic, there is only one peak in DSC, that is at 75 to 80 degrees Celsius, this one peak. This is heating scan where I get only, okay, this is of C14 homologous, I get only one peak that represents only melting. There is absence of any symmetric phase on heating scan. While in cooling, I get two peaks. One is for isotropic to symmetric, that there is onset of symmetric phase. And second peak is symmetric to crystalline, that is at quite low temperature, around 54 degrees Celsius. And next is TGS thermogram. TG is analyzed just to thermal stability. Yes, we are working with heating and cooling scans. We should know our thermal stability of compound. And my compound is thermally stable up
સારું કામ છે.
to 300 degrees Celsius. This is
ગુજરાત
DFT study.
છોડવું પડે સારી સારી
All
જોઈએ
the density functions calculations were performed using the Jaguar program package. The molecular geometry is well investigated with the compounds were fully optimized in terms of symmetry and B3 and B3 631G star developed here. Basically, these homologo interactions and entities are done to provide further support to the work. These are characterization. Thank you.
આ બધું યાદ કેમ ન રહે આ બધું યાદ કેમ ન રહે
અરે આ લોકો છે ને બહુ કરે છે આવી રીતના ઓરલ ના હોય અમારે આવશે 1 મહિના પછી અમારું છે સેશન ઓરલ
શું
મેં તો બીજો ટોપિક ચૂઝ કર્યો છે નહીં
કોન્ફરન્સમાં છે
200 માર્ક્સ એક્ઝામ છે
ઓકે ફાઇનલ યર પ્રોજેક્ટ
Slightly basic condition basically come out with
થીસીસ સબમિટ કરવાની છે થીસીસ સબમિટ કરવાની છે
ના એ નથી હવે એ નીકળી ગયું હા પ્રેક્ટિકલ આવી રીતના ઓરલ પ્રેઝન્ટેશન ઇન્ડસ્ટ્રીયલ ટ્રેનિંગ વાળું 21 એનું એ થઈ ગયું એનો રિપોર્ટ અને સાયન્ટિફિક રિપોર્ટ આવી જ રીતના કોઈ ટોપિક ચૂઝ કર્યો બનાવવાની છે
પ્રેક્ટિકલ
Basically,
એક કોન્ફરન્સ અને પ્રેક્ટિકલ પ્રેક્ટિકલ તો ઓછા છે
find power and then after that our party is based update 24 hours 16 hours dehydrating agent છે આમાં પણ યુઝ આ dehydration reaction actually sir liquid crystal material એક જૂનો કામ કરવું right now તો ઘણું બધું
It's
application
a question
હવે આજે
of
મૂળભૂત
his
application
first
કરવા તો બહુ ઓછું છે ડેવલપ કરવા માટે
એટલે મેં એટલે બેસ્ટ મેં આમાં પાર્ટનર નથી મને એક્સપિરિયન્સ છે આનો
એમાં લો બેન્ડિંગ લિક્વિડ ક્રિસ્ટલ એટલા માટે પ્રિપેર કરવાના છે કે કોઈ પણ મોલેક્યુલ જ્યારે આપણે લિક્વિડ ક્રિસ્ટલાઇન મેટેરિયલમાં યુઝ કરશું જે 1970 માં 5CP નામનો કમ્પાઉન્ડ લિક્વિડ ક્રિસ્ટલ ડિસ્પ્લેમાં યુઝ થઈ ગયો ઓલરેડી
તમારા ટોપિક
તો એની પ્રોપર્ટી 28 ડિગ્રી સેલ્સિયસ ઉપર લિક્વિડ
મારે તો મારે
ક્રિસ્ટલાઇન
ઓર્ગેનિક
તો એ ડિસ્પ્લે ટેકનોલોજીમાં સારી રીતે વપરાય
ફાર્મા
Meanwhile,
મટીરિયલ
many
એના
of
ઉપર
these applications during this time,
બહુ બોલવું
40-50 years માં develop થઈ ગયા. Like watches ના glasses માં અંદર liquid crystal display વાપરી શકાય, but they should be at low temperature, and we are working on it. And low temperature કરવા
આમાં
માટે
તો basic field જ export થાય ને medicine માટે.
romantic માટે molecular geometry should be constrained. એક આપણે માટે અમે different ortho substituent ની બનતી લઈ આવીએ અને molecular geometry ને optimize કરીએ અને low bending liquid crystalline compound બનાવીએ. Liquid crystalline material
સારું છે પોતાનું સ્કીન કે બનાવી દેવાનું
એની અંદર different effect આપી શકાય. Specifically જ્યારે આપણે chiral center જ્યારે introduce કરીએ આમાં twisted pneumatic type ના structure પણ આવી શકે છે. But it is my future work. I am trying to be. Right now મેં ખાલી linear change મારી જોયું છે કે melting પણ low થાય છે. પછી જો chiral center મને એમાં મારા future work માં કરું તો એમાં મને twisted low melting synthesis of low melting liquid crystal compound. That is aim of my PhD work, and I am trying to get hopefully.
એક જ ક્વેશ્ચન પૂછ્યો
આના 10 માર્ક્સ પણ પીએચડી
That's the oral presentation by Justice Sharma from Medical University.
મિનિટ 15 મિનિટ लास्ट हो गया
उसके बाद क्या है?
खत्म
दुख नहीं है
कुछ नहीं
सुना तो
પોસ્ટર
वो तो बात થઈ ગઈ
થઈ ગયા પૂરું બસ પૂરું જમીન છે જો
ऑफिस वाला निकाल देसे
તોય
Good noon to all.
અમારી કોલેજમાં
For
ક્યારે
a
ચાલુ
start
કરે
my
છે
presentation, I would like to thank
Busy
all the
में रहा होगा।
professor of MG Science
अगर
project.
स्टैटिस्टिक में
Because
तो
as I am
क्या
standing in front of you on this international platform, they are the pioneer of my entire journey. I am MG student. I completed my PhD in 2016 from this institute of Department of Chemistry. Here I learned many things, just completed my coursework, chemistry, everything, but also I learned wonderful lessons of my life, such as from Jatin sir, the effort he has put in the class to make us understand each and every chemical reaction change that helpful for me today also. And SN Chala sir, Suman sir, calmness, today also work for me to being and handling that whole institute with calmness. And peer pressure ideas concept are really unforgettable for me. Today also it helps when I am getting and analyzing IR spectra and minimum stereochemistry class, that is top, but
11
English at that time we are understanding. So I am thanking all the supporting staff also for being contributing to my life.
because fees
Now I am presenting my seminar topic, that is synthesis of some alpha-oxybenzoic acid. Here I have taken two moieties. One is alpha-oxybenzoic acid, 50D-methyl ester, and another one is the triazole propoxyl phenyl methylamine and their antimicrobial evolutions. Okay, today it contains introduction, aims, objectives, synthesis, characterization, its antimicrobial studies, conclusion and future scopes with references. Before going or synthesize any molecule, first of all we know that what is application for us. So when I start to think that what topic I will take, then I come across one phenomena, that is AMR is not just a medical issue. In today's life, it became a silent pandemic. So when I see this data that in 2019, 1.2 million lives are globally claimed,
whereas the projection in 2050 it's 10 billion, means it is multiplied by 10x. Here it's not just affecting us in different way, but also it affects on global economy. That is a fall of 2 to 3.5% GDP rates. So I decided to take this topic as an antimicrobial active molecules. So before going to the synthesis, first of all we have the understanding of AMR. What is that? In general topic, if we know that the germs will not longer respond to the existing drugs, at that time that word AM is coined. In PM Modi in Mann Ki Baat also he told that antibiotics are falling today. What's the reason? Because the germs get resistant to the existing drugs. One or two reasons are that when the doctor prescribed us for three months course, just we are completing 1 month and left, then the germs get resistant over that existing drugs. Then again when we are getting the same issue, the drugs is not effective, so it gives rise. In short, if I coin AMR in Gujarati that dawa asar nathi karti, that is the main motto, that dawa asar nathi karti, just the germs get resistant over it. So need for the new antimicrobial agents are added. Now, my main aim is that the drug-resistant microorganism by identifying new and effective chemical components. And the objective I have taken two here different quantities. One is piperidine alpha-oxybenzodic acid and another is triazoles, and compared to both the antimicrobial activity by characterization also. Then the synthesis part includes two main steps. One is first the addition of alkyl chain by replacing OH by alpha-oxy group, and then coupling with DCC EVAP in CHF, and we are getting the final product. The change is of alkyl chain here. In controlled conditions, here the main name reaction acidification is named as Trichal acidification, where DCC and DMAP have crucial roles. DCC is helping in the formation of as an toxic agent and removal of water molecule, whereas DMAP is used for the transfer of acyl group. The second triazole has two major steps completing. One is same as introducing the alkyl chain, and second the moiety of 1,4-amino triazole coupling by speed-based mechanism. We have synthesized 5' molecule on further, and we have done the characterization of NMR and FTIR that confirm the structure of the moieties. Then we go for the antimicrobial evolution that done with Agarwal diffusion method. We have shown ZOI there and growth tradition method MIC. Then we get the result as some components show moderate to good activity, whereas triazoles are showing more enhanced antifungal activity. Then the conclusion is that viscosity improved when the membrane penetration is done. Then second AICR observed. Then successfully we have synthesized novel compound with their characterization is confirmed. Then antimicrobial promising activity is there, and triazoles are better performance all over. Then future scopes we can go for these moieties and structural modifications and in vivo antimicrobial studies, then toxic and pharmacokinetic evolution, and lastly the molecular logging. For your attention.
સ્ટાર્ટિંગ સેલેરી કેટલી હોય?
અહીંયા તો બહુ ઓછું હોય. જો તમે R&Dમાં કોલેજ પ્લેસમેન્ટ સારું આવે આવશે તો પોતાના પર એક અહીંયા એક કંપની છે બેકસ્ટાર, મેં બેમાં ઇન્ટરવ્યૂ હતો ત્યારે મને પેકેજ એકનું 8 લાખ કીધું, એકનું 6 લાખ કીધું. બે જગ્યાએ સેમ જ પોસ્ટ પર ડિપેન્ડ કરે છે કંપની પર. પણ ત્યારે મારે ચાલુ થતું સેમ 3 તો મને ના પાડી કોલેજ.
8 LPS સારું જ કહેવાય ને?
હા સારું જ કહેવાય, પણ જોઈએ પાછું રિવ્યૂ બધા શેર કરે.
Completed our oral presentation. The 12 paper presented here, and the result for 3 best oral presentations will be declared in our validity section. Thank you very much for participating. Thank you very much.
વેલિડિટી ફંક્શન